Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends, to your younger brothers and sisters who would want to take up engineering in the future, and to your relatives. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Hello, future engineers. Welcome to my YouTube channel. And to my students, subscribers, and viewers, here is another video in Engineers in Progress, particularly on locating the centroids of not only triangles but also quadrilaterals and the derivation of the formulas for the centroids of triangles were discussed in the preceding slides, preceding videos. So I hope that this will add to your knowledge, thinking skills in solving problems in engineering. So here is the first problem. Prove that the triangle with vertices A 3, negative 6, B 8, negative 2, and C negative 1, negative 1 is a right triangle. Also find the area and the vertex angles B and C. So for the proof, I'll just present one proof, and let's apply Pythagoras theorem here, and for the sides, lengths of the sides, uh, distance formula. For the area, we can, because this is a triangle, if you can apply 1/2 base times side, then let's do it. If not, let's apply area by coordinates. For the vertex angles, let's just form right triangles, find the slopes of rays or sides, then we can find the angles. So that's problem 21. This is problem 22. Let's focus first on problem 21. So I present the solution not in PowerPoint form with animations in order to solve 3 problems on this video in a short pace. So let us show that this is A, which is at 3, negative 6, B, which is at 8, negative 2, and C at negative 1, negative 1. So let us show that side AB quantity square plus side AC quantity square must be equal to side BC quantity square. So I put question mark because we have to show it first. For AB, the solution for the length of AB, it is equal to square root of quantity 8 minus 3 square or 5 square, which is 25, plus negative 2 minus negative 6. Negative 2 minus negative 6 is positive 4 square, which is 16. 25 plus 16 is 41, therefore AB is square root of 41 units. AC, on the other hand, this is the computation of the distance. So we have negative 1 delta x, so negative 1 minus 3 quantity square, so that's negative 4 square, which is 16, plus negative 1 minus negative 6. Negative 1 minus negative 6 is positive 5, and positive 5 square is 25. 25 plus 16 is again 41. So side AC is square root of 41 units. BC is square root of, this is the calculation, square root of negative 1 minus negative 8. So negative 1 minus 8 square. So quantity negative 1 minus 8 square, negative 9 square, 81. Then plus quantity negative 1 minus negative 2. So negative 1 plus 2, which is positive 1 square. So 81 plus 1 is 82. So BC is square root of 82 units. Then let us show that it is a right triangle. In fact, it is an isosceles right triangle. So AB square plus AC square, is it really equal to BC square? Square root of 41, which is AB. square is 41, plus square root of 41 quantity square, which is AC, is also 41. 41 plus 41 is 82, and square root of 82 square is 82. Therefore, because the lengths of the side satisfy Pythagoras theorem, therefore, this triangle ABC is a right triangle. Then we proceed to compute the area of the triangle. Because it is a right triangle, the area is 1/2 product of the perpendicular legs. So 1/2, the perpendicular legs are AB and AC, and each is square root of 41. So 1/2 of square root of 41 times square root of 41 is equal to 41 over 2, or 20.5 square units. So that's the area. For the vertex angles, so first, the slope of BC is, we just take it from here. So 1, positive 1 over negative 9. So 1 over negative 9. Let's just make it positive 1 over 9. Inverse tangent using your calculator there. This is, by the way, calculator aided. Inverse tangent of 1 over 9 is 6.34 or 340 degrees. So again, 1 over 9 is 6.34 degrees. So also this angle that side BC makes with horizontal is also 6.34 degrees. Then we compute lengths of angle that AB makes with the horizontal. So we have slope 4. This 4 here is taken from here, delta y. Negative 2 plus 6 is 4. And this is 5. So that's why you have 5 there. So 4 vertical, 5 horizontal. So we can compute this angle with your calculator. So inverse tangent of 4 over 5 is 38.66 degrees. Therefore, angle B is equal to 6.34 degrees plus 38.66 degrees. So angle B, 6.34 degrees plus 38.66 degrees, and that is 45 degrees. As expected, because this is an isosceles right triangle. So we also expect that this is 45 degrees angle C. So prior to the calculations, this angle is 6.340 degrees, as explained earlier. For the slope of this triangle here, this is 4 units. 4 units is 3 x coordinate of A minus x coordinate of C. So 3 minus negative 1 is 4. Or simply, we count 1, 2, 3, 4. Likewise, the vertical projection of AC is 5. And to get 5, it is upper y negative 1 minus negative 6. So negative 1 minus negative 6 is positive 5. So, or the other way is count 1, 2, 3, 4, 5. So 5. Therefore, this angle, the measure of this angle is inverse tangent of 4 over 5. Inverse tangent of 4 over 5 is 38.66 degrees. So we can now compute angle C. Angle C is 90 degrees. So that's horizontal, vertical, 90 degrees minus 6.34 degrees minus 38.66 degrees. So therefore, angle C, 90 minus 6.34 minus 38.66. So angle C is also 45 degrees. So that's it for that problem 22. Problem 21. Let's proceed to problem 22. Find the centroid of the quadrilateral whose vertices are 0, 0. So this is 0, 0, 3, 5 there, 3, 1, and 0, let's go back, 0, 0, 0, 4, 3, 5, which is that, and 3, 1. So it happens that 4 minus 0 is 4 units, 5 minus 1 is 4 units. So therefore, we have parallel sides and equal. This is a parallelogram. And for a parallelogram, the diagonals bisect each other at the centroid of this quadrilateral, which is a parallelogram. In the second part, let's generalize this. What if it is not a parallelogram? So let's locate the individual centroid of the triangle by dividing it into this manner. But before that, since it is a parallelogram, the intersection of the diagonals is also the point or the centroid of the entire quadrilateral or the entire parallelogram. So therefore, x sub c is the average of, let's consider these 2 points, 0 plus 3. So remember midpoint formula, 1/2 of quantity x1 plus x2. So 1/2 of 0 plus 3 is 3/2. The midpoint of the diagonals of this parallelogram is also the centroid of the entire parallelogram. Then 1/2 of 4 plus 1 is 5/2. So it is 5/2. The other way is it is also the centroid. The midpoint of this diagonal is also that centroid there. So 1/2 of 3 plus 0 is 3/2. So it's still 3/2. Then 1/2 of 5 plus 0 is 5/2. So it's the same. It's the same. 5/2. Another way of solution. Then we generalize the solution by treating this as we divide this into two triangles. This triangle here and that triangle there. And since this is a parallelogram, either of these diagonal divides the parallelogram into two equal areas. So that's why if this is area 1 and that is area 2, area 1 equals area 2 equals 1/2 of, this is 4 units, and that is 3 units. 1, 2, 3. It's very obvious in the figure. Just like this 4 units, and that's 1, 2, 3. 3 units. So they are equal. Area is 1/2 of base 4, height 3. 1/2 of 4, 3 is 6 square units. So the total area therefore is 2 times 6 or 12 square units because area 1 equals area 2. Then remember the centroid of a triangle. So for triangle 1, it is 1/3 of x1 plus x2 plus x3. So 1/3 of 0 plus 0 plus 3. And that is equal to 1. So the centroid of this triangle is the x-coordinate of the centroid, x sub c1 is 1. Y sub c1 is 1/3 of 0 plus 0 plus 4 plus 1. So 1/3 of quantity y1 plus y2 plus y3 is 5/3. So that's, this point is at 1, 5/3. Then for area 2, the centroid x sub c2 is 1/3 of the x coordinates, sum of the x coordinates, 1/3 of the sum of the y coordinates. For the x coordinates, 0, then plus 3, then plus 3. 1/3 of quantity 0 plus 3 plus 3, that's 2 units. So this centroid is x sub c2 is 2. Then y sub c2 is 1/3 of quantity 4, then plus 5 plus 1. 4 y, the y coordinate of that point, plus the y coordinate of that point, which is 5, plus the y coordinate of this point, which is 1. And that is equal to 10/3. Then by Varignon's theorem, total area times x sub c equals area 1 x sub c1 plus area 2 x sub c2. Then total area times y sub c equals area 1 y sub c1 plus area 2 y sub c2. So for x sub c, total area 12 times x sub c equals area 1 6, x sub c1 is 1. Then plus area 2 6, x sub c2 is 2. Computing for x sub c is 3/2, which is the same as that. Then for y sub c, total area y sub c equals area 1, then y sub c 1 5/3 plus area 2 6 times y sub c 2 10/3. So computing for y sub c, it is 5 halves. So therefore the centroid is indeed at 3 halves, 5 halves, solved in 2 ways. So for problem 23, find the centroid of the quadrilateral whose vertices are 0, 0, 0, 4, 3, 5, and 5, 1. What is the area of the quadrilateral? So let's generalize this problem by dividing the quadrilateral into triangles, and then we use Varignon's theorem as the final solution in locating the centroid, because it is no longer a parallelogram where we can conveniently compute or determine the centroid. So let us say this is the centroid. I divide the quadrilateral into 2 triangles. This is the dividing line, the red one, and this is the other area, area 2. So area 1, we can apply 1/2 base times height. So this is 4 units, and that's the height, 5 units. So 1/2 of 4 times 5 is 10. That's area 1. Area 2, on the other hand, imagine we enclose it with a trapezoid, this trapezoid here. So it is, this one is 1 unit, obviously. And to compute that one, it's y coordinate of that point, upper minus lower, 4, so 1. For the x coordinate, obviously it is 3, but it is 3 minus 0, so it's 3. Therefore, this area outside the trapezoid is 1/2 of 3 times 1, so it is 3 halves. Then for this triangle here, which lies outside, this is right x 5 minus left x 3, so that's why it's 2 units, or simply count 1, 2. Then for the vertical leg, 5 minus 1 is 4. The other way is should be count 1, 2, 3, so 4 units. So area of this triangle is 1/2 of 2 times 4, so that's why it is 4 square units. Therefore, area 2, which is this shaded triangle here, is equal to area of trapezoid minus 3 halves minus 4. The area of trapezoid is 1/2 base 1, which is 1, plus base 2, which is 4, and the distance between bases, 5. 3 plus 2 is 5. So 1/2 quantity base 1, 1, plus base 2, 4, then times height, 5 units. Then minus 3 halves minus 4 square units. So therefore, it is area 2, 7 square units. The total area, area 1 and area 2 combined, is 10 plus 7, 17 square units. Then for this triangle here, the x-coordinate of the centroid x sub c1 is equal to 1/3 of quantity 0 plus 0 plus 5. So 1/3 of quantity 0 plus 0 plus 5 is 5/3. Y sub c1 is 1/3 of quantity 0 plus 4 plus 1. 1/3 of quantity 0 plus 4 plus 1 is 5/3. So the coordinates c sub 1 is at 5/3, 5/3. Then for x sub c2, 1/3 of quantity 0 plus 3 plus 5. So that's why it is 8/3. Y sub c2, 1/3 of quantity 4 plus 5 plus 1. So that is 10/3. So y sub c2 is 10/3. Then by Varignon's theorem, total area 17 times x sub c, coordinates of this centroid for the entire quadrilateral, is equal to area 1, 10 square units, then x sub c1, 5/3, plus area 2, 7, then x sub c2, 8/3. Computing 10 times 5, 50, plus 7 times 8, 56. 56 plus 50 is 106. 106 over 3 over 17. 3 times 17 is 51. Therefore, x sub c is 106 over 51. In decimal, using your calculator, 2.078 units. Likewise, 17 times y sub c by Varignons again equals area 1, then y sub c1 5/3, area 1 is 10, y sub c1 5/3, plus area 2, 7 square units, then y sub c2 10/3. So 10 times 5, 50, plus 7 times 10, 70, plus 50, 120. 120 over 3 is 40. 40 divided by 17, so that's y sub c. 40 over 17, or approximately 2.353 in decimals. Therefore, the centroid of this quadrilateral is at x sub c 106 over 51, comma, y sub c 40 over 17. So that's it for this video. I hope that you gain important knowledge in algebra, location of centroids of quadrilaterals.